Let's learn representation theory on TikTok. This is part 2, and you remember in part 1 we had these two matrices here. And I explained that they're basically just permuting the entries. And if you've taken a course in abstract algebra, you know that the word permute is often associated with what we call the symmetric group. Now, if you have 3 things, I'm calling them 1, 2, and 3, there are 6 different ways that you can permute them. You can do nothing, you could just swap 2 of them, or you could take all 3 and kind of move them around in a circle. And there are 2 ways to do the circle, and there's 3 ways to swap the pair. Now, I've drawn arrows with what this operation A and operation B are doing. So this first blue one was swapping 2 and 3, and then the red one was doing that cycle. So basically what I've done is I've represented these 2 kind of abstract permutations specifically with matrices. I've represented them. That's exactly what I want you to think of. When you think of a representation of a group, it's just a way of identifying every element of the group with a matrix so that the rules they obey are the same. This really is the way I want you to think about it, but really also what we're doing is we just have a homomorphism from our group G to the group of invertible matrices. Now, in abstract algebra, you learn that a group is a set that's closed under multiplication and every element has an inverse. That's why we're mapping here to invertible matrices so that we can be sure that every matrix we get actually has an inverse. Now, the size of the matrix, we're going to call that the dimension of the representation. If you remember in your abstract algebra class, you probably proved lots of properties about homomorphisms, and we're going to see those in action. But in the rest of this video, I just want to do lots of examples. And so in that symmetric group S3, remember those 6 permutations. To give a representation of this, I just have to give you 6 matrices that obey all the rules that the ones on the left do. It might sound like a lot of work to do this. We have to write down 6 matrices after all. But in this example, if we call this element B, then we work out what B times B is, we actually get this element. And then if we call this element A, well, if we square it, well, if we swap 2 and 3 and then do it again, that's just the identity. And then when we work out what A times B and B times A are, it turns out that A and B generate this whole group. So really, if I can write down a matrix A and a matrix B that satisfies all the rules over here, then, if I need to fill in this, I just do A squared. Here I fill in B times A, etc. So really I have to write down 2 matrices, but they have to satisfy a lot of properties. And we're going to see what that looks like. The example that started this series with the blue and red matrix, if we fill in all of these, we get what's called the permutation representation of S3. It's 3-dimensional because the matrices are 3 by 3. It's a lot of work, but you can check that all of the rules satisfied over here are satisfied over here. I keep talking about rules. What are the rules? Well, every group has what's called a presentation, which means there are some elements that generate it. In this case, A and B generate everything. But then those elements satisfy rules. We call those relations. And for instance, one relation is that A squared is the identity and B cubed is the identity. And if I multiply AB, it's the same as doing B squared A. You can check all that if you check your permutations and see how things multiply. But since those are the rules on the left, they have to be rules on the right as well by that homomorphism property. Again, say we're doing a 1-dimensional representation, I just have to write down 1 by 1 matrices that obey these rules. Well, what's the entry of the blue matrix? Well, if A squared is 1, there's really only 2 numbers. It could be 1 or minus 1. And then if you think about what B could be, well, in the complex numbers, there are actually 3 different numbers that B could be. But if you play around with 1 by 1 matrices, which are really just numbers, this equation here actually forces B to either be 0 or 1. And since its cube has to be 1, it's got to be 1. And so actually, there's only like one option for what this matrix has to be. It has to be the matrix 1, whereas we do have that option of A being 1 or minus 1. It was a lot of calculations, and I promise you, if you try doing it with 2 by 2 or 3 by 3 matrices, it's like way, way, way harder. The good news is we just found 2 different 1-dimensional representations. Back here, we found a 3-dimensional representation. But if you remember in our first video, by playing around with that 3-dimensional representation, we saw that we could find a basis so that those matrices decomposed into these blocks. If you just look at what's happening above this cross, it's saying, well, why don't we send A to the matrix 1 and B to the matrix 1? That's precisely this representation I wrote down over here. And if we look at what's under the cross, it suggests a 2-dimensional representation by sending the element A to this 2 by 2 matrix here and the element B to this one down there. Now, I wanted to make sure I didn't make a mistake on TikTok, so I checked that all 3 of these properties are true for these matrices. Check it yourself. I think that's good practice. Let's abstract this a little bit. What is it we did? We started with a 3-dimensional representation, and we decomposed it, and we got 2 things, one of which was fairly boring. It was just sending everything to 1. But the other thing was kind of interesting, and we hadn't found it before. The big questions in representation theory are asking how many different representations does a group have, what are their dimensions, and like when are two representations equal to each other. We're also going to study what it means for a representation to be irreducible. In other words, it can't be broken down into smaller pieces. We're going to learn some cool ways to actually do calculations, like with actual numbers. Check all of these things. It's going to be a lot of fun. If you made it to the end of this video and you find this content valuable, it really helps me if you can put a comment in there or if you can recommend this video to a friend.